And now I can tell you about curvature. So when we have a space curve or even a curve in the plane, it will generally curve, bend, and to express how much it curves, we can use a quantity called the curvature, which can be computed using, again, vector functions, vector function which parameterizes our space curve. So we've seen before that we have something called the unit tangent vector, and what curvature is, so curvature is denoted by the Greek letter kappa, and the way it's computed, by definition, it's the derivative of the unit tangent vector with respect to the arc length parameter. So first you have to move to this arc length parameterization, compute the unit tangent vector in terms of this arc length parameter, take its derivative with respect to that parameter s, and take the length of that derivative. So, but there are easier ways of computing this. So if you don't want to do this work of switching to arc length parameterization, you can just use any parameterization. All you have to do is compute the derivative with respect to any parameterization, so any parameter t, divide and compute its length, and divide that by the derivative vector's length with respect to the same parameterization. Okay, so that's a second formula for the curvature. And there is an even perhaps easier way, which only uses the vector function r, and that would be the length of the cross product of r prime and r double prime of t. So what you do is you differentiate your vector function once and twice, take those derivative vectors, form their cross product, compute its length, and divide that by the length of r prime t cubed. Okay, so either one of these three formulas will give you the curvature of your space curve, which tells you how much it bends, basically telling you how much it differs from a straight line. So just to give you an example, Q3, I will ask you the following question. What's the curvature? What's kappa for a circle of radius A? Okay, so what's kappa for a circle of radius A is your question. Pause the video and input your answer below. Okay, I hope you paused it. So just to get a circle of radius A, I mean, it's quite easy to parameterize a circle of radius A using the trigonometric functions. So A times the cosine of t, A times the sine of t will give me a circle of radius A in the xy plane centered at the origin, and by having the third coordinate be 0, it's really in the xy plane. So all you have to do now is you have to compute these different quantities. Maybe I'll just go with the second formula. So first I'll compute the derivative of rt, which is just minus a times the sine of t, a times the cosine of t, and 0, of course. Compute its length, which in this case is going to be fairly simple, as all you have to do is just take the square root of the squared sum of the components. But again, we can use the famous trigonometric identity that the sine squared plus the cosine squared gives you 1. So all you get is a. Okay, so when you look at the definition of the unit tangent vector, well, that was just this derivative vector divided by its length. So that's this derivative vector, this derivative vector divided by its length. So that's just 1 over a times minus a times sine of t, a times cosine of t, and 0. So multiplying by a gives you minus the sine of t, cosine of t, and 0 for the components. So the length of this, now we have to differentiate that unit tangent vector with respect to t. So let's do that. We'll get minus cosine of t for the first component. The second component is minus sine of t, and the third component is of course 0. So its length, the length of the derivative of the unit tangent vector, is just the squared sum of its coordinates under the square root. Again, famous trigonometric identity. The sum of squares of cosine and sine is giving you 1, and indeed in this case this is the length of the unit of the derivative of the unit tangent vector. So now we can indeed compute or write down the curvature of a circle of radius a, which is this quantity. We're computing everything. So the length of t prime is 1, and the length of r prime is a. With this, we have the curvature of a circle of radius a is 1 over a everywhere. Okay, so with that, we have covered what curvature is. Now, there are a few more related vectors that one can be computed and are useful in studying space curves. Not just the unit tangent vector is what we need, but also something called the unit normal vector and the binormal vector. So these are computed from RT, of course. So the unit normal vector is going to be perpendicular to the unit tangent vector. It's going to be orthogonal to it. That's why it's called a normal vector. It's perpendicular to the curve, so to speak. And you compute that by basically differentiate. So this is denoted by capital NT, and it's obtained by taking the derivative of the unit tangent vector and making it into a unit vector by dividing it by its own length. So that's the unit normal vector. And the way you compute the binormal vector, which will be a vector that is perpendicular to both the unit tangent vector and the unit normal vector, is just taking the cross product of these two. So this is called the binormal vector, and it's denoted by capital B of t, and all you have to do is just take the unit tangent vector and take its cross product with the unit normal vector. Okay, and this binormal vector will be basically the normal vector for the plane in which the curve, the plane which is closest to the curve around a certain point. So that plane is spanned by t and n, and b is a normal vector to that plane for the space curve. Okay, so let me give you a last question, is to compute the unit tangent vector, the unit normal vector, and the binormal vector for a given space curve. So my last question is to compute these quantities, capital T, capital N, capital B, for the space curve given by, parameterized by the vector function that is that has the components, the cosine of t, sine of t, and t. Yes. Okay, so actually the first, well, let's just do this. So first we need the derivative of, pause the video and input your answers below. And if you paused it, what you could have done is just computing the derivative of RT first to get minus sine of t, cosine of t, and 1. Well, you need its length to get the unit tangent vector, and that will be, as we've seen in a previous question, was root 2. Okay, so the unit tangent vector is just the ratio of these two, so it's 1 over root 2 times minus sine t, cosine of t, and 1. Now, to obtain the unit normal vector, we have to compute its derivative, the derivative of the unit tangent vector. Just differentiating each term will give us 1 over root 2 times minus the cosine of t, minus sine of t, and 0. And we have to compute its length, the length of the derivative of the unit tangent vector. And if you do that, you will notice that it is indeed 1 over root 2 because of the usual famous trigonometric identity. From these two quantities, you can cook up, you can just divide one by the other to get the unit normal vector, which is just the derivative of the unit tangent vector divided by its length. So exactly that factor of 1 over root 2 will cancel, leaving us with minus the cosine of t, minus the sine of t, and 0. And in the last step, we want to compute the cross product of t and n to get the binormal vector, just like this formula tells us. So to get b of t, we need to compute the cross product of t and n, and of course that will be that can be done with the usual determinantal formula minus. So we have I, j, and k in the first row. We have the components of t in the second row. So these are 1 over root 2 times minus sine t, 1 over root 2 times cosine t, and 1 over root 2. Okay, and in the third row we have the components of n, which is minus the cosine of t, minus the sine of t, and 0. And if we expand, if we compute the cross product, what we get is for I, the basis vector I, we get 1 over root 2 times the sine of t. For j, we get minus 1 over root 2 times the cosine of t, and just that. So minus 1 over root 2 times the cosine of t, because the other product gives you 0. And finally, for the k component, we get again 1 over root 2 times the sine squared of t, plus, so minus 1 over root 2 times the cosine squared t, but that's just 1 over root 2. So let me just write that like so, but that is, by the famous trigonometric identity, is just 1. So indeed, the components of bt are 1 over root 2 times the sine of t, minus 1 over root 2 times the cosine of t, and 1 over root 2. With that, let me stop here, and I hope you enjoyed this video.